IT. You need to go to IT. No, it should be on. So it's on, but is it showing it? It should be showing whatever I have there. It should be there. Anyway, I need somebody to. Oh, there it is. Oh, magic touch, eh? Okay, I have the attendance switched on. So if you are a new student, there are no new students here. Oh, there are here. You need to download this Griffith attendance app and run it for each lecture that you will run. Because, yes.
My phone is broken, so I can't do the attendance double.
Okay, I'll take your name manually today. You know what?
This message.
Yeah.
I will not the app, but always.
And instead of that yellow mark, you should get a green one that says you've been.
Yes, but it has not worked on the precedent class. It works, but for the class.
Okay. Okay, I can take your attendance manually, yeah?
We all don't have access to Moodle yet or anything.
You don't have access to Moodle yet?
We are
In this place, looks like you need to push to get your, you know, so you have to go to the office. I don't know what the reason is.
We already wrote emails, we already were over there.
Go to the office and tell them, listen, we can't start. Okay. The program director is Barry. Send him a strong email. Say, I need to be, you know.
Can you give me
What? Yeah, Barry Dempsey, I think. I don't know if this is I or E. You check him in the website. Okay, who knows Barry Dempsey's email? To previous students. Nobody knows him. He's your program director. You have his email?
It's
DE, is it? At Griffith. .ie. He's your program director. So you should point all, you know, problems, grievances, solutions. Ask him for a solution, an immediate solution, because time will go, and you know, every week you're going to start getting more work and more work. But it's not fair. Anyway, I'll take your attendance now. If you can see the pictures here, if I can make these pictures a little bit bigger. No, nothing is bigger here. Maybe let's get rid of this.
I think we should.
Pictures don't get any bigger. Okay. Albert, I just call the names quickly, and if one of your names. Okay, Albert is marked in, Alex is marked in, Anderson. Now, Arthur. We have Arthur? Arthur, are you here? Put your hand up.
No, he's not.
Okay, Ashwin, then Brio. All right, I'll mark you present. Right, so you're marked present now for today. Okay, I'll just go to the ones who are not here. Ho Ching Glan, you're not here. Hugo Duval?
Yeah.
Yeah? Thank you. Right, so I've marked you present. Nathan Diaz? Yeah. Okay guys, you're registered. It looks like you're registered on there. So just download your app, the app, and run it, and it should do it automatically. Okay. Right, try to sort it out as soon as you can. Okay, the next one is Sahid Abdul Razak, Sahid is not here. Vinicius Pepe Belome. Yeah. Oh yeah, I remember you. Okay. Is everybody here? Is everybody? If your name is not here, then I'll give you a piece of paper to write your name. Everybody has seen their names or their image or their picture? No?
No, so it's us seven. So that row over there, because we're from Germany, and yeah, we haven't had.
Don't worry, no problem. We will sort it out. But for today, you need to write your name for me.
Yeah.
Okay, if your name is not on the list, just write here the date at the top and write.
Yeah, we also have like a reference number that we usually put on there. You put it last time.
No, this is every time. Okay. Right, so that's attendance out of the way. I'm going to call it out or leave it until I'll save it and we'll do it later. Save, switch room, no, save attendance. Perfectimo. Right, I'm going to Zoom. I've opened the Zoom room. Nothing seems to be working this semester. Normally they have good record, IT. Blur my background, I don't want to blur it. Integrated, yeah. There it is. Is this? Yeah, okay, that's fine. I'm gonna get rid of this, guys. There should be another device here, it's not here. I'm gonna ask them to change the room or install the device. If it will work, if not,
Max, schreibst du mir jetzt eine E-Mail oder?
we all right, let's get moving. Let's not wait for the right equipment all the time, or else we'll do nothing. So today I'm going to talk a little bit about switching techniques, very briefly. And what we mean by switching technique is how information is moved from one machine to the next, from one end to the other end. So end-to-end operation of movement. And I go briefly through them, but you need a good general understanding. And once you understand it, we can, check features or advantages or problems with them. So, generally, it's called, switching techniques. And the first technique that was used in computing. When computers started, they started exchanging information. They started just having transmitter at one computer and a receiver at the other thing, just send the full file in. So it's called message switching. Message switching. It's a real old technique, it's no longer used, but that's how it started, and we see how it developed. Right, so the technique started this way. If you have a file to send, this is back in the 60s, like, I don't know, 40, 50 years ago, the computer started, you want to send a file, you take the file, you start your transmitter, start transmitting that file through wire or radio signals or whatever it is to another computer, the whole file, a bit at a time, just keep transmitting. And of course, you can't keep all that file without some storage device. And in the old days, they had tapes, so they were writing the file onto a tape. But for now, let's just say it's an external storage device. It could be a hard disk, but you're sending the file. And when the full file is transmitted all the way, complete, correct, without errors, then they finish with this and they start sending it to the next computer. It could be 100 kilometers away, whatever, transmitters and receivers they have. It could be 1,000 kilometers away if satellites, but then probably there was no satellites for communication. But anyway, you had to send the file and write it and keep sending it from one computer to the next until finally you get the final destination. It can take hours to send a file, hours. And the main reason is that first, maybe transmission speed wasn't as good, but also you had to write this information onto an external storage device, which is a mechanical device, a tape or a hard disk, which are very, very slow compared to main memory. So that's the way the first, data transmission technique that was used by computer companies on the computing technology. But soon, maybe in the 70s or 80s, they changed it, they developed it, improved it. And it was tremendous improvement. It was a big jump, big change in speed of transmission. And just by simple technique, they said the main reason this technique is slow is because of the mechanical devices. Get rid of them. Send the information right through main memory. Main memory, just so you need to know, or you already know, of course, that main memory, electricity travels through wires and through main memory at the speed, almost the speed of light. So it's very fast. Mechanical devices are, compared to electronics it's like the speed of a rocket compared to a horse cart. That's really the difference in speeds or the ratios. So they said, they got rid of this technique and they started a new technique and they called it the datagram switching technique. And that's obviously you heard of it because this is the technique that's in use today on the internet. That's what the internet uses. It's a development of the message switching technique. So what's the main idea on this one? They say put a maximum limit on the message size. You cannot send a whole file in one go. That doesn't work anymore. So what they did, they said if we want to send information inside the main memory, then the message has to fit in main memory and therefore it has to be small. So this is now the datagram switching technique. So if you have a file to send, break it into smaller units. We call them datagrams or we call them packets. That's what we use today in the datagram. And with every packet, you put a header. On the front of it, you put some more information. What are the information? Source address, destination address, and sequence number. That's like 1, 2, 3, 4, and so on. And that's what datagram uses right today. Takes your file or message they want to send, break it into small units. We call them packets or datagrams, put a header. Of course, there's more information goes in it. But for now, at least those 3 pieces of information are necessary. And give them to the nearest router that you have. Routers are your gateway into a network. A network normally in all our textbooks nowadays, they draw a router something like this. They show you the infrastructure, the inside main devices of a router, of a network. And usually we show the users are all connected to a router. Maybe you and your neighbors are all connected to a router. So at home you might have a link or connection to a router or gateway, whatever the name they call it. It's your kind of router that connects you to the rest of the world, to your network. And then, so this is the way we always draw networks in most textbooks. You'll see the users around it, and on the inside, this is the actual infrastructure of the network. So, this is the datagram switching technique. To send a file or a message, break it into smaller units. We call them datagrams. Append a header or put a header on the front of each packet and fill this information. Each packet will carry its own source address and destination address and sequence number. And we just give them to the nearest router. We don't ask it, we just say, here it is, deliver this. And the router can never say no to you. It just takes the packets and finds out, and looks at each packet independently. So every packet is separate from the other. It says, where do you want to go? And it looks and finds the address on it. So it says, okay, it looks at the IP address, that's the IP address. Say maybe that's the best way to go. Let's say you want to send a message to this guy here, that device. So it picks this address, this machine. So right, this is the best route. You're going to send packet number 1, 2, 3, 4. Maybe they all go in this direction. It decides, the router decides, maybe this link has a higher speed, maybe it's in the right direction, maybe they both will get there, but one of them is busier than the other. Maybe after a few seconds this becomes slow, so decide to change. It might send packet number 4, 5 this way, and 6 and all that. And when this one gets it, might say, all right, that user there, you better go this way. And maybe this is, a good enough route. Number 1, 2. This might be a twisted pair, so it's a slow wire. So I say, no, I better go through maybe a fiber optic this way. So it might send the rest of the data this way. So the idea is that eventually all the packets will get to the end. But they might get out of sequence. And eventually when they all arrive here, the user will put them, make sure they're in the right order, and gets rid of all the headers that they have. So it removes the information that was added here by the sender. They're deleted by the receiver. We just take the user data, join them together, and that becomes our file. So that's now how messages are actually transferred from one source to a final destination. They're broken into small, why are they broken into small packets? So they'll only fit in main memory. So in fact, a message now going from here to Australia, going from my computer, the main memory of my computer, straight to the main memory of the next router, to main memory of the next router, it will fly so fast we get to Australia in less than a second. It used to be hours. It used to take hours to transfer this information. And this is really the biggest breakthrough, in communication, in practical transmission. So now we can send information so fast using the datagram switching technique. You need to be able to describe datagram switching technique. If you're asked, describe it, usually there's maybe 4 or 5 statements altogether. First one, you want to send data, you break it into small units. We call them datagrams. A datagram has a header that's added to it that self-contained. It has its own, the address where it needs to go, the address where it came from, and it's a sequence number. Every router deals with every individual packet on its own and finds the best way to forward that packet. Packets might go the same route, but might follow different routes. But they'll all hopefully get to the destination. And when they get to the destination, the receiver will arrange them if they arrive out of sequence and hand them over to the user. So that's basically how it works. Now, datagram, I'll just mention a few things now, they'll appear later. It does not give you any acknowledgement. It does not tell you, the network or the system does not tell you, the datagram switching technique, does not tell you whether the packet was delivered or not delivered. That's called acknowledgement, positive or negative, but there's no acknowledgement whatsoever. And also, it doesn't tell you if it got lost. And also, If that address he gave is wrong, it'll just go there. If it doesn't find the address, just disappears and that's it. If you forget how datagram works, which you won't forget, but if you do, think of the postal system. It's just like the ordinary post, not the register post, not express post, just ordinary post. Like you go on a holiday to Mallorca and you send your friend a postcard and you drop it into the box. That's what happened. Or here you want to send a letter to your friend in Australia. You want to send 10 letters, one every day. And you might mark them. This is letter number 1, 2, 3. And so that's like packets. And you put them in the post office. The post office, the way it works here in Ireland and every country around the world, they collect the post and they say, right, we have a letter for Australia. Do we have a direct flight to Australia? It's like, do we have a direct link to that router? No, we don't. Well then, send it in that direction towards Australia. So send it to London. We have a direct link to London, Paris, I don't know, Rome. So we pick one of them, London, because maybe there's lots of flights there. So we'll be sending information to London. And London gets the same thing and say, oh, this one is going to Australia. Let me forward it to Paris or Istanbul. Maybe there's no flight to Istanbul today, put it to Paris, and so on. So it keeps going. So tomorrow's letter, your letter tomorrow, the post office gets it. Maybe there's no flight to London. They might say, okay, let's send it straight to Rome. And from it, they can deal with it. So it goes to Rome. So all the posts going to the same destination, they might follow different routes based on what's available, the situation. Maybe there's strike over in France, so we'll avoid it, we go somewhere else. And that's the way the postal system works, and that's also how datagram switching technique works. The ordinary post, again, if your postcard or that letter did not get delivered or got lost, you don't know. You don't know whether it has been delivered to your final destination or not. Maybe your friend at the final destination gets it and sends you a letter, an acknowledgement, but that's not acknowledgement from the system. The system looks at that as a separate message coming back in the opposite direction. It's not an official acknowledgement from the network. These links here, like there are a few keywords. Are they shared or dedicated? It's important to know, are they shared links or dedicated links? In Datagram, all links are shared. So that's a good thing sometimes. There are other networks that have dedicated link. Which one is better? Is it better to have a shared link or a dedicated link? What's the advantage, or what do you think? Do you think shared links are better or dedicated links in a network?
I feel it depends on the situation for
Okay. Give me one situation where you say shared is better for this reason or dedicated is better for this reason.
Dedicated better for security.
Security. Okay. From a security point of view, nothing is secure. Once it leaves your machine, it's not secure. Whether it's dedicated or shared, anybody who wants to pick that information, they should be able to pick it. Okay, let's get again. What do you think? Which one is better? Shared or dedicated links in a network?
I'm sorry, I don't have an answer.
Okay, yeah?
I think shared is faster because
shared is faster?
yes, because with all the routes possible, the data might be bigger to
Okay.
the user.
All right, I'll interrupt you here. Shared, if we have a channel here, it can carry 100 million bits per second. If you want to use it, all this 100 million is yours. Whether you use it or not, it's available to your... If you share it with 100 other people, then everybody will only be able to transfer 1 million per second. So if you have it dedicated, it's faster from a user point of view. So if you get a dedicated link, then the full capacity of that link, the speed of that link is available to you. It's faster. So if in Datagram here, it's shared. For example, if you're watching a video, like most people are using the Datagram switching technique. So if you want to watch a video, then you're downloading the video from some server. These are all the users or servers. So a server will be sending you that video you're watching. And you watch for maybe about 10, 15, 20 minutes, and then suddenly things start interruptions. Interruptions because the links that are shared, now people decided to start using them. And the more people that use these links, the more data transferred, the less then is left for you. Or it's normally split. It's like traffic in a street. If you drive at night or early in the morning, there's very little traffic, so you can drive fast there. But if the traffic gets heavier and heavier, you might have to stop at every crossroad and all that. So the capacity of the link, in this case here, the datagram, the full capacity of the links in a network depend on the number of users. The links are shareable, and there's no limit to how many users can share it. So, and that's why datagram never provides or never guarantees something called quality of service. Quality of service, sometimes it's good or sometimes it's poor, depending on the amount of data being sent, the number of packets being sent, the activity on the network. And because the links are shared, you must suffer the consequences of more users who are using it. So that's another point about datagram switching technique. And this is what the internet uses today around the world. So and therefore, quality of service is not guaranteed using this particular method of exchanging information because the links are shared. But give it one thing about the routing, it's flexible routing. So flexible route. So if you're traveling, we're sending your data this way, and then this router finds this place, this route is getting a little bit slow, it can switch to another route. So routing is flexible, and it can pick the best route available at that moment of time. But when the packets arrive at the end, they could be out of sequence, out of the sequence of packets received. Sequence received it can be a problem, so that it needs another application to reorganize them. Of course, acknowledgements, just right here, acknowledgements, no acknowledgements. Error detection, no error detection. So this is what we have at the moment. There's a service that does not provide acknowledgement, does not provide error detection. If a packet is lost, it's lost, and it doesn't tell you that it is lost, it's received. And the quality of service can never be guaranteed. It depends on the number of users. So these two techniques here, the message switching is obviously no longer in use, but it was developed by computing companies, and then the datagram was developed by, again, computing industry to improve it. And they've improved it a lot, and it's the most used technique today. So now I'm going to talk about two other techniques that are also not necessarily in use, but I'm going to start with a technique called circuit switching. Circuit switching is the old telephone systems. You remember, telephone companies have been around for 160 years now, maybe 150 years, and since telephones were introduced, and they feel that's our business. Communication is our, the telephone industry's business. And these computing companies are coming up and taking over. So they try to improve or come up with their own technique of communicating. So we look at their old technique first. So circuit switching technique is the way telephones used to work, not necessarily now. So just so you get the idea of how they improved, the same as we looked at message and then developed into datagram. So the circuit switching technique, the way it works, if there is a street in every city, every street in every city, in every area, there are houses, and every house maybe used to have a phone, right? So there'll be lots of phones in every street, and in every street there is a box, and they're still there. But they used to be mechanical boxes, now they're electronic boxes, and they call them switching boxes. That's where the name switch came from, switching box. And every phone has two wires going in the street, going to that box. And there'd be dozens or hundreds of wires going into each box in every street. And there's another street there, and there's another box with all the houses in it. And also another street, there's another box, and there's another box. And the city is full of boxes, switching boxes. And they're all connected together. So this one might be connected to that box with two wires, this one connected to that, and connected to that, and so on. So each one of them is connected to so many other boxes. Because remember, if you want to talk to somebody over the phone, they're kind of the way you connect phones. There are maybe two famous ways of communicating. You either have a direct link with every other phone, which is impossible, but that's the best way. If I can have a phone or a pair of wires going to each one, then I can call anyone. But that's impossible to have. That's a huge cost, and the size of that network would be impossible to build. The other technique is to broadcast. Anytime you want to send a message to one person, you broadcast it. This is how local area networks now mostly work. You broadcast a message and say, that's for number 17. Everybody gets it, but everybody looks out. I'm not 17, except number 17 will take it in. And then when 17 wants to send me a message, broadcast it again. So these are the two techniques, the extreme techniques. Broadcast your message to everyone and let the individual intended party take it, and the others ignore it, or have a direct link with everyone. And both of these techniques are not good. So switching is, the telephone companies long time ago came up with switching, which allows you to talk to anybody in the city or in the world without having to have direct links and without having to broadcast. So this is the way it does. So they had all the boxes connected together in many parts of the city. And for example, and here there's another box here, another box there, and these are all the phones in another street. So now the idea is that, let's say you want to communicate with somebody. This phone here wants to talk to that phone. How do they do it? So you need the number, the phone number for this one, like 703, whatever it is. So this guy picks up the phone, is how it is describing the circuit switching technique. The circuit switching. The caller must first, this consists of 3 phases. This communication consists of 3 parts. The first part is called call setup. You cannot talk, you cannot send data until you do this part first. That's establishing a link or contact with the other device before you start sending data. And we still do that basically, even in the newer technique in telephone systems. Even now with your phone, you don't pick up the phone and start, hey Tom, how's it going? No, you have to dial Tom, call Tom, and wait until Tom accepts your call. And then you can start sending data. Same with computing. A computer wants to send data to another computer, must first dial it or call it somehow, establish a link with it, logical link, because physical links are already there, and then start sending data. So this guy starts dialing the number, the signal goes to the first box, and based on the numbers, the switches, they kind of rotate one on top of the other to make sure you're linked to which of those boxes will be the best one. Let's say this is the better box, so you get a link from here, the rotation goes, and you get connected to that one. So now there's already a link to this switch, and really to this switch as far as this switch is concerned. And then the rest of the number causes this switch to also rotate, and it picks up, say, it turns the switch into this direction, so it's linked to this switching box, and this switching box maybe eventually is the one that's all these phones are connected to, and it rotates the switch, and now it connects you there. And once it reaches here, it's like you have an electric circuit, a full electric circuit between this machine and that machine, and it's designed in that it will start ringing, or indicating to the sender, to the receiver, here's a call for you. And like in the older days, that's all it says. There's a bell ringing, and once this picks up the phone, that means they've accepted the call, and that's the end of the call setup. So the call setup starts by this one dialing a number, and that number will guide these switches to make physical contact, the real two-wire contact, all the way to the end, to the final machine. It starts ringing. Once the receiver picks up the phone, that means the call setup is on. Now you can send data. So the second part is data transfer, or communicate, talk if you want. But you have the link now. Now, while they're communicating, as you can see here, there's a channel, there's set up a real electric circuit set up from this machine to that machine. And this circuit is dedicated to those two users for the duration of the call. No one else will share it. Like if another user here wants to communicate with another user there, and they have to pass through this wire, they'll get a busy signal. So for now, let's say if there's one wire, there's one call on it, even though there's multiplexing that allows us to have 10 calls or 100 calls, but this is the basic idea. There's no sharing. So let's stick to that. So in circuit switching technique, you dial a number, you get connected to the far end through a number of switches, but it's a direct link, it's a direct electric circuit in such a way, while you're talking, if this circuit is broken or opened at any point, you lose the call. The whole circuit electric circuit dies down. So there is no flexibility. It won't work if part of the system breaks. While in the datagram switching technique here, imagine if you are sending your datagrams to through this link, and for some reason this link breaks. You won't know about it, but this router will change to another link and send your packet to a different link. So there's that ability is called robustness. A system that has robustness, or a robust system, is a system that will continue to work even if parts of it are broken. If a part of the system breaks down, the system will continue to operate. This is a good feature to have. Datagram has that feature. So if one link breaks, it will continue. But in circuit switching, if part of the main circuit that you're talking to, like if there's a call, an existing call, and breaks down, that call is terminated. And in order to continue it, you must start a new call. You cannot continue that particular call. You must start redial another one. So this is the old way that how phones worked. It's called circuit switching technique. And it's the only technique that has the wires are not shared, they are dedicated during the call. So it uses dedicated links for, this is the circuit switching and this is the datagram switching technique here. But the quality of service, because you have a dedicated link, it's fantastic. The whole capacity of the channel, the power of the transmitters and the channel, the capacity of the channel is available to one user. So it has the highest quality. So if you want to watch a video, would you rather watch a video using circuit switching or datagram? And anytime we mention the word video throughout this course or in communication, if you hear video, it means a lot of data and it needs to be transmitted at a good speed. Otherwise, it will start interrupting. So videos are synonymous for large amount of data and at high speed. So you need a network that delivers large amount of data at a high speed in order to watch a video without interruptions. So videos are a measure of quality of service. So if you're watching a video, maybe circuit switching is a better way to watch it without any interruption. With datagram, and be careful, datagram does not have a poor quality. Sometimes it has good quality, but cannot guarantee it. And it cannot guarantee it because it never says no to users. While here, if while you're on this call, other people will be blocked out. Anytime someone else wants to call somebody and say, sorry, busy line, or whatever, they tell them, but there's no call. You have to wait until the line becomes available in order to carry that. Okay, so that technique can only support one call per line, give or take. This one, datagram, can support 10,000 calls per line. That's the difference between them. So the datagram switching technique along this way can be, data coming from another user going to another user, but they're sharing the same link, or maybe another user here, so receiving. So the same link can be shared by maximum maybe a large number of around 10,000 users, because you're only sending packets. So you send a packet from this user, another packet from another user. So all the packets are lined up in a queue and they just sent one after the other. And the router decides where each packet will go. But that's how good it is. So from a network point of view, if you want to set up a network, and make business and make money, you're better off setting datagram switching technique, because you can have 10,000 people and you only charge them €1 a day. That's 10,000 euros a day. Okay, they'll have bad quality of service, but that's okay. That's not, your problem a lot. With this one here, circuit switching, you can say, listen guys, we're going to have a fantastic quality of service. But remember, only if you get the call. Otherwise, you could be wasting a lot of time waiting to get the call. But when you get it, only when you get it, that you have a good quality of service. So, and if you get it, then we have to charge you, because the other 10,000 people are not paying for that. So one person has to pay for it. So it's a lot more expensive to run, even though the quality is great. But over the last 50 years, people have been saying, just get me a connection to the internet. It doesn't have to be so good. I'll accept poor quality at 10 euros a month, which is very reasonable, or 20 euros a month, as compared to this one here. So telephone companies, they realized that's not a good technique, but they didn't give up. They improved it. And they started a new technique, and it's called, so this technique is no longer kind of run today, except maybe in some very, maybe back countries that didn't have any communication, that maybe in England and France, they say, okay, we don't want that now anymore. Yeah, you can have it. And they give it to someone else for free, but it's obviously for not great quality. So the next now technique that's available, it's called virtual circuit. Virtual circuit. So telephone companies still using a circuit, but it's not a real circuit. Anytime you hear the word virtual, it's like virtual reality. It's like near reality, but it's not exactly reality. In this one here, virtual circuit's like a circuit, but it's not a real circuit. So how does this work, and what does it look like? So of course now we have, instead of these switches that I had earlier on, they're like routers. They still call them switches in those kind of networks. And similar to this one here, the users will be connected to those networks. And again, let's say user A, he wants to talk to user B and send or communicate or exchange videos or whatever it is. So in this technique, you also need those 3 phases that the circuit switching technique used. Do you remember what those 3 phases are? In order to send data in the circuit switching technique, what's step number 1? Call setup. So you must do a call setup. And then number 2 is send data transfer, and do data transfer. And then number 3, clear this call clear. Just like phone calls. Start a phone call, talk, and then hang up. Clear that call, close the call. They still do that in virtual circuit. But this is the way it works. Now, if you have a file to send, obviously now it's there are data networks that operate in this technique, in virtual circuit. So what you do is also, they use datagrams or packets, but before they send them to the network, first they send one packet, and it's called a call request packet. So, and what do you put in that call request? You put the addresses. A wants to communicate with B. What's the address of A? What's the address of B? So source address and destination address. And something one bit to indicate this is a request. I want to talk to that one. Right, so usually with bits, you have a byte here, one of the bits indicates I'm calling this guy request. And if this guy turns the second bit to 1, that means I accept, or 0 to refuse, but simple enough. So it's very simple, very small packet that goes out to this router. Now, every router has a table in its memory of all the calls that are running now, or all the calls that can run. Usually about 10,000 calls. 5 to 10,000 calls. One table in memory, and it has 5,000 records or 10,000 records, depending on how many calls you can have. And each call, for example, say X is communicating with Y, and usually, as you can see all these users connected to the router. Each connection here, what do they call them? Call them a link or a port. Let's say we call it a port, right? So these ports are numbered, so they know A is in port number 7, whatever it is, this guy number 8, that's number 9 is connected to another router, and so on. So, for example, it says, yeah, here's X, and X is communicating with Y, who is here, a user here. So this guy has it there, and the call is continuing, and this one is busy, and this is maybe number 1, 2, 3, number 12. This is record number 12. So, and there's so many other calls, but there are few of them are free. There are no call. The call is over, finished. So now, when A sends a request that wants to communicate with B at this router, goes around and looks for a free record, a free call. So it goes, finds one here, say, okay, great, that's free. That's X wants to communicate with Y. And where did I get this link from X? Let's say X, we got it there at port number 7. And okay, I'm going to decide, is it that way or this way? Where's the best route? Same as what every router does in the datagram for every packet. They do this for only the first packet. Let's say decide, okay, this is a better way to send it. That's line number, port number 9. So I say, if I get anything on 7, I'll send it to 9. And now instead of free, this is a call is being requested. So there is a request. It's not really a full call yet, but it's just a, and forwards this packet to this one. So this one gets, but now notice it's record number, what did we say? Number 27, right? This is record number 27. So that's an important number to remember for this particular router. And the packet is forwarded to this one. This one has its own table as well. And maybe a record 128, or that's 119, there is a free record for a call. So it puts, it says, okay, X wants to communicate with Y. At my port, this is port number 3 came in. I'm going to send it 4, 5. I'm going to send it to 5 to this one. And writes it, and that number is, this is like if you want to go on a holiday. This is the nearest thing to this is like going on a holiday. Before you go, like this one, before we send the data, we send a request. So let's say from Ireland, you want to go on holiday to, I don't know, somewhere in Tokyo, in Japan, right? So first you say, right, I need to fly. I need to fly. There are very few flights here from Dublin, so I go to London. So first thing you call Aer Lingus and you say, I want to book a flight to London. So they take all your information, your name, your passport number, everything, when do you want to travel, and then they book you flight from Dublin to London, and they give you that booking code. So yeah, that's the booking code that you take. So you take that number. And then you go again and book flight from London to, let's say, Istanbul, from British Airways. You call British Airways, you make a booking, and they also give you another booking code, see, 119. That's your booking code for the next flight. And then you get to Istanbul, and then you keep doing that, and for every jump or for every airlines, they give you their booking code. We call that booking code, we call it the virtual circuit number. Yeah.
So this kind of open record list, what would we use? What word would we use to describe it? Like, is there a specific type of vocabulary that we call this list, or?
Virtual circuit calls list for each router. All the calls that are happening through each router. Every router keeps a list of all the calls that are going through it. And when they're finished, or when maybe requesting is just about to start, when it's ongoing, maybe and then when it terminates, it just makes this free. Right, so anyway, so the point is every airline will know about your trip and your family. And they have all your details. They know where you're going, when you're going, and what's your next stop and all that. And they also need to, see, it keeps you came in at number 7. This is port number 7 on this. And you're going at port 9. And this one knows what port you came in at number 3, maybe at number 5, and so on. So now you've planned all your flights or your holiday or whatever. And this is what happens to this request. It goes from one router to the next. And every router will know about your call. It hasn't started yet, but your packet eventually reaches your final destination, B, and this guy, as part of the algorithm, he has to accept or refuse. The call comes in or a request, accept or refuse. And either way, it just sends probably the same packet backward with maybe bit number 3 turned into 0 or 1, accept or refuse. Whatever it is, doesn't matter how it's accepted, but let's say it's got accepted. So the packet will follow back, go back to this one we know exactly where the packet from and go and update that now the call is open for the A and B, sent back to this one, it knows exactly which line to send it back, and this guy marks this as now it's on, this call is busy or whatever it is, the code they put in, and then comes back here. So the point is every airlines, if you are booking a holiday, knows about you and they have confirmation of your booking. Now, we get back to here. The acceptance comes in here. Now, what it means, it doesn't mean we booked, let's say this is the booking that happened. You're going this way from here. Okay. So now you go that way, let's say this way and that way. This is the route that has been booked for you. But it's not dedicated, it's not for you. The rest of the flights are flying every day those routes, carrying hundreds of other passengers. But whenever you want to go, that time, the day you come in, let's go back now to the datagram. Now once we get the acceptance, we take our file, break it into packets, and every packet we put a header, but this time we don't have to put the source destination, the source and destination addresses. We already know. All we need is this code that we were given here, which is 27. So we just put 27 and a sequence number 1. And this one 27, sequence number 2, and so on. So the number, virtual circuit number, that's the one we carry. And now every packet, we just send it to this router, and this router will look at it and say, oh, 27, it will check it's stable, 27, oh, I know who you are. You're X and you're going, well, A or B. You're X and you're traveling or you want to communicate with B. You came at port 7, I'm going to send you to port 9. So it just brings the packet here and transmits it to the next one. Of course, it will change the number, the virtual circuit from 27 to put 119. So when you get there, imagine you're traveling, you go to the airport. If you're now traveling from Dublin to London, and you arrive, you already have a booking, just like this, what this packet would do. You get to the terminal, you want to check in. They don't ask you, what's your name? Say, where's your booking code? You give them the booking code, they enter and say, oh, they have all your name. They know you're going to London. They don't have to ask you any more questions. They just say, go get number 26 or 15 or whatever. You go get, that's like the port. Like a router is like an airport, guys. For us humans traveling from one airport to the other, the packets are like they travel from one router to another. You get to the next router, of course, this router will change that booking code 27 to the new booking code we got from this one, 119. We get there, you get to London Airport, you go to British Airways, the desk say, I have a flight somewhere. They don't talk to you, just give us the booking code. 119, they enter it, they know who you are, they know where you're going, they direct you to the correct port, and you'll travel then to the next point. So that's how it works. So now, let's just finish this part here. So now, all the packets will have one number, 27. That's here it's called the virtual circuit number, and a sequence number. So you send them, and every router knows about them, gets there, this guy removes the sequence number and the header, and hands or, transfer them to their user, and they have the file. Did you have a question, somebody there? I saw a hand going up, yeah?
So that log table, the one that has all the virtual numbers and everything, is that stored in the packets? Every packet has a log table, or when it's sent?
Every router has a table, its own table.
Yeah.
And when it books a record or a call, it gives you that number. And you need to put that number on every packet you send. And every packet will be following the same route.
So both the packets and the router has its own table. Both the packets and the router has its own table to know the destination and
the packet doesn't have a table. The packet is just a piece of information, like a bundle, like a person traveling. And when you get to the airport, the airline will say to you, where's your booking code? So that's exactly what the packet is going, and in front of it, here's my booking code, here's my virtual circuit number. If it gets to the router, it shows its virtual circuit number. The router will do that. There's a program in the router, a small app that checks the routing table, finds that number. It says, all right, yeah, I know who you are. I know who you're communicating with. and you came at this port number 9, I'm going to transfer you to this port and send you transmit it to the next one. It'll actually change your booking code, removes the 27 and puts 119, and send you to the next router. Because that's the booking code for the next router, for the next airlines. Any more questions? Right. So, why is this good now? And it's good. First, when a packet is sent from one machine to the next or from one router to the next, it's error checked. If there's something wrong, it'll say, can you send it back again? There's something wrong with it. So they built in error detection. Also, because of that, then you know it's moved and there's an acknowledgement. So it has an acknowledgement, it has error detection. Almost guaranteed it will be delivered. If it fails once, twice, you know, keep trying. There's a maximum number, of course. Now, if this link goes down, your call is terminated, same as the previous one. They had a standby route, but I just want to talk about the basic operation of a virtual circuit. As it started and the basic operation, if this link breaks, then your call is terminated. What else? How come this one can guarantee quality of service and the datagram cannot? The datagram can never guarantee quality of service. The reason is that as the number of users increase and the use of the network increase, it's just there's no limit. There's nothing that stops them. Here, when you send a request to this router can say no to you. The refusal doesn't have to come from the end user. Maybe the first router will refuse you, or the second, or third. If this router, it says, I can handle 10,000 calls, and right now I have 10,000 calls running, then it will not accept 10,001 call. It will not accept another call. Why? It says, okay, that's what my processing power, my memory, is enough to guarantee good quality of service for this number of calls, no more. So even though the lines are shared, but there is a limit to how much users can share them, who can share them. With the datagram, there is no limit. But with this one here, it stops the number of sharing the link in such a way that you will always have a good quality of service. That means if you watch a video using this kind of network, you'll never have interruptions. The quality of service is guaranteed to a certain level. While with the datagram, it's not guaranteed. Okay, so these are the 4 techniques. 2 of those are in use today, virtual circuits and message switching, datagram switching. But datagram switching is taken over, basically. It's just the reason, because it's very cheap, because the requirements on the devices, see, these devices here need to be reasonably powerful to do error detection, to do acknowledging, to maintain this quality of service. While with this one, they don't do most of that work, and therefore any machine of any power can be plugged into the internet and works. Okay, the quality will not be great, but it still works reasonably okay. So, and most people for the last 40 years, just get me a connection, or maybe 30 years, just get me a connection onto the net. I know it's not the best, but it's better than nothing. Especially if you're only doing emails and simple messages. You're not really going to watch videos successfully or watch TV channels, stream them down. This one would stream down TV channels, no problem. But datagram switching technique would not be suitable for that. So these are the actual 4 switching techniques. So I'm going to show them to you. Any more questions? Okay, maybe I'll ask a few questions. Yeah, go on.
All of them be used like in the same network. All of them datagram and virtual circuits.
Say again?
All of them use the same network.
No, not on the same network. Generally, usually nowadays, they used to be available. Maybe 15 years ago, you can get virtual circuits, but they became not available to householders, not to the end users. They're still up at the high level of, maybe they deliver networks for communication network companies rather than, like they take delivery of data from, say, Europe to maybe to Asia or Tokyo or Japan or China. There'll be different companies that will say, all right, we'll take that, but I think they became slightly expensive for end users, for us people. And also, it started improving a little bit because of the speed improvement in technology. Datagrams started improving, but unfortunately more users started using it. And every program that comes in your app needs more data. So we're still having the quality of service problem.
Yeah, what would a modern example of a dedicated link be? Because like most...
Let's start again.
So most networks use datagram switching, right?
The datagram switching.
Yeah. So most networks would also use a shared link. But what would like a modern example?
No, I don't think dedicated link would be a successful public thing because it's way too expensive.
Are there like any niche use cases where it would be?
Well, maybe military implementation or something like that, but I doubt it. It's way too expensive. It used to be, even maybe still up to today, you can go to the post office in any country, in Europe at least. You say to them, listen, I need my own dedicated link between my branches. A bank may decide I want that. Yeah, but they'll pay for it. Like they'll pay 50,000 euros or something a year for a dedicated line.
So it's like more of a company, like...
Yeah, some companies might. They used to be. More companies 20 years ago. I'd imagine there's less and less nowadays. No, dedicated is really, from a commercial point of view, they're not successful. Like, as I said, in the datagram switch technique, you can have 10,000 users using one link. That's almost the cost difference between, a dedicated and a shared link. So they're way too expensive. Now, yeah.
For the datagram switching techniques, you said that quality of service was an issue.
In the datagram?
Yeah.
Yeah.
If you are adding more and more nodes, will it be better or will it still be an issue?
Don't think so, because you have no control over the number of users or how much users they can, who share. Well, if you limit the number of users, then now you're getting into, controlling the number of users. The difference between them is that one can stop new calls when they reach certain levels. With this one, it does not. This is the internet, guys. The internet is it. So in the internet protocol, there's no request. You don't go and ask them. You can just give them the data to the network, and the network has to deliver it. They actually call it best effort service. That's what they give, the guarantee they give you. They say, we do what we can, the best we can. So there's no guarantee. So definitely, if you need a good quality of service, you need to look for other than the datagram if there is a way.
The virtual circuit also has robustness, or is more difficult? I mean, if a link goes down?
If a link goes down in the datagram?
No, in the robust.
In the virtual circuit?
Yeah,
in later implementation, they said, okay, when you make a call, we'll get you the best route, but we'll also give you a standby route immediately. So if this fails, we'll switch to the other one. But what I'm talking about, I'm talking about the basic implementation, so you know the ideas. But it's still a secondary solution. It's not the real. So what if the second route goes? Then your call is terminated. While the other one, you just switch to another link if there is.
So modern technology, does it use datagram in virtual circuits?
Which one?
Modern technology.
Modern technology, both. Well, end users, datagram is probably 80% of the world now use datagram. Only certain organizations, some universities, maybe certain companies, they might still decide we want to go for virtual circuits, but it's becoming less and less available to end users. But there are companies behind the end user that take from data companies and deliver their data, to Africa, to Asia, to like the motorways. The highways of the data is probably run by virtual circuits. The end users' houses is still low speed, low quality of service. Now my question is, if you have a company, and let's say you had a choice, there are two networks at your door. You want to use this network or this network. If you had an advertising company, which switching technique would you use? Virtual circuits or datagram switching technique? Datagram. Yeah, that's a good answer. Yeah, why is a good question. That's my next question. But it's a good answer, it's the wrong answer, datagram. But I'd be interested in knowing why. Who said datagram? Or sorry, virtual circuit. Okay. Why datagram?
First of all, it doesn't limit the amount of data you can send, and it can send to as many nodes or users as possible.
The other one, once you get the call setup established, there's no limit on the amount of data you can send. Actually, you probably can send more data with it, quicker data with this way, if you get the call set up.
Yeah, but for virtual circuits, it can be more expensive for the company.
Okay, I'm assuming you have this multi-million company that does just advertising. These two options are available to you, yeah?
They don't need to accept the call. They don't need to accept the transfer, so I can just send.
Yeah, that's the. If you are advertising, like for example, a shampoo company says to you, "Here's shampoo, advertise it for us." You want to send it to 10 million people. If you use the virtual circuit, then you have to call every individual one of those 10 million people. Send a request to their computer. There's a message appears on their screen. Do you want to, can we talk to you about shampoo? Most likely, it's going to be no. So they're not going to even see the ad. While with the datagram, we don't give them an option. You just send it to them. They get it in their either email or whatever it is. The message appears to them. Here's the best shampoo you can use. So in this case, just setting up the call, guys. Let me get back to setting up the call, especially with the circuit switching. Yeah, with the circuit switching, the one before computing, with the circuit switching, where you get dedicated line. And be careful. This virtual circuit is not dedicated line, it's shared line, right? It's about 10,000 people maybe, but there's a limit to the maximum. The only technique that uses a dedicated link is the old telephone system, that's the circuit, where they try to establish a call with you, and once it's established, it's a dedicated link for us. We can talk as fast as you want, or send as much data as we want, as much as the link can handle. But the problem with that, so that quality of service is fantastic, but the time it takes to set up the call. Setting up a call, like calling somebody, is that an advantage or a disadvantage? See, so with the datagram, they say, hey, you want to send a message to somebody using this supposedly fast technique. How long will it take you to send a request and receive a response back, especially with the old phones? With the old phones, remember, they used to be manual. It probably took 10 seconds to set up a call. Or if you're calling somebody so far, say on the other side in Australia, and in Australia, not in the city of Sydney, somewhere else down a village somewhere, that they only have 2 phones or 3 phones, it'll probably take you 30 seconds to reach that phone using the old technique, the old system. And by the time you establish the call, this datagram can send a message. Remember, this one can send, if it's not busy, it can send a message in a second. So by the time you set up a phone call with this to call the receiver and get their okay, the other one could have sent it. So, if I ask which one is faster to send a message? Datagram or virtual circuit? I'm not saying which one gives you that good quality of service. We know that one guarantees it, this one does not guarantee. But which one is faster to send one message?
Just to send the datagram.
The datagram. Anybody agrees?
Yeah.
Why? Okay, it depends a little bit on the size of the message. Does the size of the message differ if you know how long it will take to send it? Or which one is faster?
Just a packet or?
No, not just a packet. The message can be a small message, hello, one word, or it can be a file. If it was a big file, 5 million bytes.
I guess for larger files, we would try to use virtual circuits.
Why?
Because once the call is set up, generally there's like less latency compared to.
Yeah. Okay, there's less likely. This one, it can be fast as well if no users are there, but There's no guarantee, and that's why if I say download a file, download a video, would it be faster to download it this way? This could be just as fast if there were no users. But because it's going to take 10, 15 minutes to download it or something like that, well, maybe over that period of time, then more users might decide to start use this network, and then they start delaying you. Well, that one you're guaranteed. So which one is faster? Which message will be delivered faster? Yes, that one has a problem of having to do a call setup. But call setup, really, with this new virtual circuit, okay, it probably take half a second or less, or even less, a 100th of a second to go all the way to Australia and get a response back. But that 100th of a second, this guy can send 10 packets. So if your message is less than 10 packets, maybe it's better to go with the datagram and hope it's not an already crowded one. Yeah, I'll be back with you. Yeah?
So basically the virtual circuit is kind of like a combination between datagram and this circuit switch.
Ask again?
Is a virtual circuit kind of a combination between the datagram
Yeah,
and
all the new ones use datagrams. They don't call them datagram, they call it the packets here. But still, yeah, these are the only two new techniques that are used today. And they both use a small unit of data, and they only use main memory. So they're both very fast, and they're both, obviously this one is more publicly used, but I think for the wrong reason, but it's improving, it's getting there. All right, let me show you those on the slide, and then if we can. Any more questions? Which one is more robust? First, what's the definition of robust? Anybody remembers what robust mean? Yeah?
Redundancy or
No, redundancy, no. Robust is not redundancy, yeah?
well, the datagram is more robust since even if a connection gets cut,
It will still
it will
continue to
still-
work, yeah.
yeah.
No, okay, what's robust, a robust system?
It's when it's not failing or we can recover from failure.
Okay, close, yeah.
With availability, credibility, and
Ooh, okay, good.
argument.
Okay, a robust system is a system that will continue to work even if parts of it break down. Even if there's a breakdown, will it continue to work? If it does, we say this is a robust system, and it's an advantage to have. In any, say, a network, if you lose few links in a network, will the network continue to work, or will it collapse? If it's a robust network, then it will continue to work. All right, let me start this. I started it earlier, yeah. I just want to change now the sharing and I'm glad. All right. I think this is right. Maybe, can you hit that switch behind it, the light switch, please? See if it'll go up. Yeah, that's perfect. Okay. The second one, put it back on, so it'll keep you awake, I'm just waiting for this to come on. Okay, is it adjustable or is it? Oh, what's it gonna break? IT. Okay. Just imagine this is The cinema in town, what's the name of that cinema that we have? All right. Okay, you can look at these later on, but this is about switching techniques and how communication initially starts by one-to-one communication. At least that's one way to pass information, is one-to-one, or broadcast to everyone. But you can't have one-to-one with everybody in the world. It'll be chaos. It'll be impossible. So there's either normally connections, either point-to-point or multi-point. This is point-to-point as well. So point-to-point, that means there's one link that you share with another machine. This is not multi-point, this is point-to-point, but this machine has one link with that machine, has one link with that machine. So this is a way how we can have one-to-way, one-to-one or link-to-link. But any more than 4 or 5 machines, it becomes almost impossible. You cannot, say if we had 40 computers, you can't connect each one of them to each and every one of other one of the 40 computers. Because the bundles of cables, you don't have 40 ports behind every device, so it's impossible. Maybe only 3 or 4 it's possible you can connect. Maybe your computer with your friend's computer, you can transfer files from one to another. But to go beyond 3 or 4 machines, it's impossible. So the other technique is broadcasting that's used in networks, where one machine B wants to communicate with D, broadcast a message to everyone, everyone ignores except D. Either of those techniques are not suitable, but you can check the cost. That's a lot more expensive. This is much cheaper, cabling wise. Speed wise, this has the highest speed because that's a dedicated link between these 2 machines. Unfortunately, utilization, that's how much are you using this link. If you have a dedicated link, you probably will not get much use out of it. Every now and again, but most of the time it's sitting doing idle. Yeah, when you need it, it's fast, but when you don't need it, it's not doing any work. While in the shared cables, it's slower because you're sharing it, but it's being used most of the time because there's always somebody who needs to transmit information. The robustness is also something good. With these ones, if this cable breaks, all communication stops, while this one, if this cable breaks, only those 2 machines cannot communicate. So this is more robust. The rest of the system will continue to work. This is where you get the word robustness. Scalability, that's mean, can we make it bigger and bigger? No, with this one, it's impossible to make it bigger. It's almost prohibitive. So, you know, it's too much. Technologically, it's not possible to have lots of machines connected together. While this one, yeah, you can go up to 500 machines connected together. The quality of service will be bad, but it works. Maintenance, it's also easier to decide where the problem is. So if everybody says to you, we can communicate, except those 2, we cannot communicate, then you can pinpoint the problem between them, this cable. So it's easier to maintain. While this one, if there's a loose connection anywhere, nobody can communicate. You have to go through all the connections to find out where it is. That's called fault isolation is more difficult with this one. Single point of failure, this one suffers from a single point of failure. You get one loose connection, all communication stops. That's a bad system. Any system that has one point, if it fails, everything stops. That's the opposite of robustness. Robustness, sometimes the whole unit stops, but the system will continue to work. So single point of failure is bad. If you ever design any system, avoid this single point of failure. When you say it won't fail, it will be the first to fail. It will always fail. Link utilization. So, you know, this is important for economists and accountants. They say, how much are we getting use out of this? The utilization is like if you, for example, if you buy an airplane and that airplane has 100 seats and you're always booked 50%. So it's calculated by how much the capacity is used by what's the total available capacity. If you own an airplane and so only 50 seats are booked out of the 100, that's 50 divided by 100, that's 50%. That's the capacity. If you're selling 90% of the seats, then your utilization is 90%. The same with communication channels. If you buy a cable and install it, and it can deliver, say, 1 million, but you're only delivering 800,000, then that's 80% utilization. So usually any money you invest, well, economical people and accountants, they tell you, if you invest this, what's the utilization for that? So they need to know that you're using that. Security, which one is more secure? None of them is secure, but this one somebody said earlier on, it's secure because it's dedicated. That's not necessarily correct. So if it's a twisted pair, it's not secure. It's radiating. Any current goes through an electric wire, any electric current going through a metal wire, as it's going, it's generating a magnetic field. It's like telling everybody, here's what I'm carrying. It can be picked up without touching the wire by, antennas, small little pickup devices, and translated into it. You can see what somebody's sending or receiving all the time. Usually they can do it by parking outside the campus, and they can see all the data that's leaving or coming back. So none of them is secure anyway. Latency is a delay. How fast is it going, or how much delay is involved in this one? Of course, this one has minimum latency or no latency at all, because just whatever the speed travels, that's almost the speed of light, electrons going from one machine to the other, while here you have to wait. If there are 100 devices and you join the queue, and you have to wait for 99 of them to use their turn before you get your turn. So there's a lot of latency in this system. So it's just a question, which one is better to use, shared links or dedicated links? That's an example of dedicated links. That's an example of shared links. And you need to know those points. Just keep them in mind. And routers are really like the airports, as I said earlier on, for us. But for data going from here to there, this is around the world. There are lots of local area networks and wide area networks, and between them there are routers. And a message going from one user to another user has to go through a router, and this router has to look for the next router, and then this router has to look for the next router, and then eventually to the final device. So any message you send, all packets will go from one router to the next until they reach the final destination. This may be kind of a nice image that shows you all the networks around the world, around the globe, and the routers that need to connect them to deliver them from one to another. This is an example of the message switching technique. This whole file sent to one computer by transmitters, receivers, stored onto each one of those devices, and only when it's fully received on one machine that it is transmitted to the next one. Only when it's fully successfully received. If there's an error, we'll ask this one to retransmit it. But then it keeps going from one machine to another and stored on external devices until it reaches the final device. That's message switching technique. This is the first attempt of computers sending data. And it's very slow and very poor. And why is it very slow? Anybody knows the reason? Why is this slow?
Because the memory storage takes time to process.
Because, the external storage devices that are used, they are extremely slow. And that's the main reason. And why can't we send it straight through main memory? Why wasn't it sent through main memory, that file? Any idea?
The ROMs are faster than the ROMs.
Répétez, s'il vous plaît. I didn't hear you. Well, I didn't understand you. I heard you, but I didn't. Okay, tell me.
Because the RAMs couldn't handle that much of.
Because the message is too big to fit into main memory. And this is really the main reason for referring to datagram switching technique. So this is really the main development from message switching to datagram. And it made a huge difference. And a big development, big revolution in speed of communication. So now, take the file, break it into smaller units, we call them datagrams, or packets, there are many names, or cells, many different networks, and protocols call them different names. But datagram, because this is the datagram, because in the old days there used to be something called telegram. Do you know what it is? In the old days, you go to the post office and you say, I want to send an urgent message to somebody, really fast, express. They say, yeah, and you write it, and they charge you per word. So you have to be very, use very few words. Like maybe, I don't know, €1 word or something like that. But there was no euro then 60 years ago. So, but they did, and they send it by radio, and the other post office receives it, and they go deliver it to the house. So when the computers company came, so that used to be a big thing. So they called this similar to telegram, but they said let's call this datagram. So, and that hence the name stuck and became a datagram. So now datagram is a small message, that's what it refers to, and we add a header to it. We add the source and destination addresses to every packet and a sequence number. And we let them go. We just give them to the first router. We don't ask, we don't request. We just say, here it is, deliver this. So the packets start going to the first router. Every router finds the best route. They don't necessarily all have to follow the same route. They can go different routes, but they'll all get there. When they get there, normally the headers are deleted and all packets put together for the final route, for the final message. Now again, another example, they might go in different routes and some of them might get delayed, and we get them here out of sequence. So this is a consequence of how it works. It's a disadvantage that you might get them out of sequence at the end. So if you're asked what's the disadvantage of datagram, don't describe how it works. So the question sometimes in the exam say, describe how it works, explain how datagram works. You say, right, the message is taken, broken into packets. Every packet contains the source and destination address, and they're given to the nearest router, and every router will find the best route and forward it to the next router. That's how it works. Disadvantages? Anybody can think of any disadvantage? What's the disadvantage of this one now compared to the newer techniques we talked about?
If one of the router is down, and if one of the router is down, the network may be overloaded. Maybe overloaded.
No, well, if this router goes down, like if we're sending them this way and this one goes down, no, we can switch to another one. So that's an advantage actually. That's an advantage, that you can switch to another route. It's flexible route.
There's no guarantee of quality of service?
There is no guarantee of quality of service. Why not? Why there is no guarantee of quality of service to datagram switching?
Datagrams are unlimited. Like there can be too many users, and
yeah.
So that's why they can't.
Yeah, because they cannot block any users, and the number of users is unlimited. Okay. Right. So let's look at another one. So you can think of datagram as the postal system. So if I say what features, what disadvantages, you say, okay, there's no guarantee. When you send a letter by post to somebody in Australia or South Africa, you don't know whether that person received it or not. There's no acknowledgement. Same in datagram. And this is also how it works. Like you get a packet going from one city to another, and that city, the post system will look at it and say, okay, we have a letter for whatever, Rome. Right, we have a direct flight, let's send it there. They could have sent it directly from London. And there are many, maybe that day they didn't have a direct flight, so they sent it through another route. Maybe they want to send it through France, but France maybe, there's a delay, so let's send it through Madrid. So each router will decide based on its communication with its neighbors, how fast the link is it up or down, is it available, that kind of thing. You decide where is the best route. Right, let's look at the next technique. Okay. Okay, this is the circuit switching technique. Where's the sound? How do you make it quite? This one here is not. Okay. So this is the telephone system. This is the circuit switching technique I mentioned earlier on. Now these are the switching boxes that are spread around the streets in every city. And few phones are connected in one street are connected to each switching box. So every street in town has those switching boxes, and all the boxes are linked together, connected together through maybe two pair of wires. This is the way it used to work. If you want to call some number, you need its. If you want to call somebody on a phone, you need its number. You have to pick up the phone and dial the number. And once the number is dialed, let me go a little bit faster here. Keep going. Yeah. So you start dialing the number, and hopefully it will move, and it will go from there. This switch will start rotating based on the next number and connect you to this another box in town, and keep rotating and get the connection maybe to this box here, and from here then connects you to the phone. And the moment you have it, you should hear it ringing, but I've made it silent. So now it's ringing and waiting for somebody to pick it up. And once somebody picks it up, it's like your phone is ringing and you accept the call. Once you accept the call, then the whole circuit appears to us that there's kind of connection between the two ends, and they can communicate. And that link from one end to the other is a dedicated link, and no one else can use it. Right? And if this link breaks, the whole call is gone. But if someone else wants to dial and this maybe call another number, and that link is busy, then it will be getting the busy call. It's the old way systems or telephone systems work. So now let's go back to the virtual circuit. So you can look at this is on YouTube. Let me get back now to. How are we doing on time? Are we finished soon? Yeah. Okay, so this is a virtual circuit switching technique. This is the old telephone system, but turned into, kind of a computerized kind of network. Again, you have a file, you want to send it over, but now you send a call request. Only a packet that carries the addresses of A and B, it goes from one router to the next. Those routers that are picked along the way, they all know now about this call between A and B. And they have all the port numbers lined up in their own, each one of them has its own virtual circuit table. And this final user has to respond, either refuse or accept the call. So if it's accepted, now we can take the message, break it into packets, and send it. Each packet will have the virtual circuit number and a sequence number. So another point here is that the header is much smaller, and they'll all follow the same route. So most likely they will never be out of sequence. More likely they will be in complete sequence. At the end, either A or B anybody can terminate the call. With the phones, you just hang up and all the switches here, I should have left the previous video, all the switches here will go back to neutral kind of position available for anyone else. Now, this is a bit more efficient as well at utilizing the channel, because remember, when you're sending a file of certain amount, you always need to send more information that's not really part of the data. And the more of extra information you send, the less efficient your network is. Because let's imagine if you have to send 1 million bits of data and you have to send 500,000 bits of extra information. That's a lot of wasted transmission capacity into non-user data. So in the virtual circuit, these packets are much smaller than in the datagram switching, because in the datagram switching, just what we looked at so far is that you have IP address for the source and IP address for the receiver. So you are carrying two addresses. Anybody knows how big the IP address is? Okay, I think there are 4 bytes for the IP4 and 16 bytes for the IP6. So you're carrying 2 addresses that's 32 bytes long. That's a lot, 128 bits each. So that's quite a big one. And that's only the addresses. There's a lot more information, as we will learn, that goes into the headers. So this one is a lot more efficient because you're only carrying 1 virtual circuit number instead of 2 addresses. Okay, so that's really those 4 virtual circuit techniques in quite a simple. All right, so a few questions just while we're at it here. Right, when will a datagram packet switch network be faster to use than a virtual circuit? Normally, you think virtual circuit is faster, but can you tell me when is it? You say, no, it's faster if we send this message or whatever it is in, yeah?
Either when no one else is using the...
If there are no one else, but let's assume same number of people are using both, for example, or the nature of operation, yeah?
Depends on packet size. For smaller packages, for smaller packets.
It depends on the message size, not the package size, yeah? The message size.
If the message is smaller, the datagram will be faster, but if the message is large, the...
Why do you think, okay, thank you, why, he's right, but why? Give me a reason why is datagrams faster when we're transferring small messages? Any idea?
We don't need to wait for a response. We don't need to, we can use different ways to communicate. We don't need to wait for one line.
Okay, that's what I'm waiting for. Waiting for what? A call setup. Okay, in the virtual circuit, you need to send first call request, get the other party to agree, and then send the message. If it's a short message, the datagram can send the message by the time the virtual circuit ends up setting up the message. But if the message is long, like a video file, possibly virtual circuit is better because they can both be fast, but datagram can have an increase, unexpected increase in number of users, while with the virtual circuit, if there is an increased number of users, they will not affect your quality of service of existing calls. Right. Is the datagram switching network better, or is virtual circuit switching network better for a user to watch a streamed video? You want to watch a video, which one is better? Use virtual circuit or datagram?
Virtual circuit, because the video will be sent in one step.
Because what?
Because the video, we will load all the video in one time. So.
Okay, the first answer is right, but the reason may not necessarily be right. Why is virtual circuit better to use for a user to watch a video?
Because there is a limited number of users, so you have mostly the full capacity to listen to talk between the
Yeah, okay. Because the quality, because virtual circuit can guarantee the quality of service. And if I say, how does it guarantee it? Because it blocks new users. If the number of users increase and you happen to be in a virtual circuit, it will not take any more users. In a datagram, it can take any number of users. So this is a datagram, that's virtual circuit. Even if you are running a race, you can run it in comfort or run it in. Which switching technique has a larger header? Datagram or virtual circuit? Anybody hasn't spoken yet? I haven't heard your voice yet. Which one has a bigger header? Virtual circuit or datagram?
I think virtual circuit has to be better.
Why?
Because it needs to send more information.
Okay, thank you. The guy in the back there. Which one has a bigger header? Virtual circuit or datagram? Datagram. Why? Why is it bigger?
The source, the destination, and this.
Okay, or why is the virtual circuit smaller? Because it only has the virtual circuit number instead of the 2 addresses. Yeah. Okay, so yeah, the virtual circuit has a smaller header. Which technique can block new calls? Which of the 4 techniques? Remember, message switching and datagram, or circuit switching and virtual circuits? Which of the 4 techniques can block a call. Like if somebody's making a call, say sorry, it can't give you that call.
This is the circuit switching.
Circuit switching, yeah, that's the old system. Anything else? What about datagram? What about virtual circuit? Virtual circuit blocks and circuit switching blocks. So the old telephone system you can get blocked, and also with the virtual circuit you can still get blocked. Yeah.
So it is connection and connectionless systems, or can we say that?
Yeah. Which one is connection? Which one is connectionless?
The connectionless one is the datagram.
Yeah.
And the virtual circuit is connection.
Connection oriented.
So we can say it is.
Yeah. That's my next question, maybe.
Oh, all right.
Yeah. Good. Yeah.
Sorry.
Yeah. Which one implements the connection-oriented communication, and which one implements the connection-less? The datagram is a connection-less. You want to send a message, you don't have to make any contacts with the receiver. Just send it and hope for the best. Right. In which technique a route is established during a call setup in the network between the sender and the receiver by making the appropriate entries into the virtual circuit table in each route. Okay, that's very clear. Okay, so yeah, you want to answer this? Yeah. Okay. Now, okay, but the question is, maybe should have been, which technique established the route at the start, and which technique will do it, for each individual packet. Obviously, the datagram, every packet, there's no set route for each router decide, oh, you are better to go this way. Gets to the other router, decides you're better off going this way. But in virtual circuit, it's determined at the start and is not allowed to change. Right, in which technique does each packet contain the sender's and the receiver's addresses and some other information? Which technique? Every packet holds or carries the sender and the receiver addresses and the datagram. What about the virtual circuit? What does the virtual circuit carry? What information goes in the header of almost every packet? Yeah, it's virtual circuit number. Yeah, we call that. I just use booking number for, just to get the idea across. Okay, in which technique do packets get reassembled into the message, which will hopefully match the message sent by the sender? So, in other words, which technique take the message, break it into small units, bring it to the other end, put it together? Which technique does that? Message switching?
The datagram.
Data. Okay, now if the question was in the exam, which technique will do this? And you say just datagram, that means the others don't do it. Okay. Which techniques would do that? Would break the message into smaller units and then reassemble them. Okay. Oh, yeah. Sorry, yeah, correct. I was thinking of circuit switching as well, but circuit switching does not. It does not require users to break the message. But when computers use them, they used to break as well, but it's not a requirement, sorry. But those two are requirements, yes. You're correct, sorry. Which technique directly supports the implementation of the Internet protocol? The datagram was actually designed for the Internet, or the Internet protocol was designed in Chubovich. Right, which technique is more suitable for remote live video and music over the net? Are you with me? Is you with me? Yeah. Which technique is more suited for music or video? Datagram or virtual circuit? Why? Which technique do successive packets from the same sender, the same receiver, may follow different routes through the network? Do packets follow the same route in the networks, or they might go a different route?
In the
Datagram or virtual
circuit switch, they do.
Circuit switch, there are no packets, but it's okay. Yeah. If we do, yeah. What about virtual circuits? Virtual circuits and datagram. That's virtual circuit, the one we were talking about here. The virtual circuit is the one you book your holiday with the route and then you're not allowed to change. So they all must follow the same route. Right, okay, let's finish this. Oh. Which technique do successive packets from same sender to the same target must follow different routes through the network? In which network the packet you say cannot follow the same route, you must go on a different route? None of them. There's nothing, no network will say, hey, you must go on a different route. They might say you must follow the same route that's in the data in the virtual circuit. The question should have been which one should follow the same route. Which technique states that if a link along the route fails, then the communication will fail? Which technique will, yeah?
Virtual circuit and also circuit.
Yeah, perfect. Circuit switching and virtual circuit. If you lose one link along the call, your call is terminated. Which technique requires that a call setup must be performed before data can be sent? Okay, yeah, go back, yeah. The last row, I was going for that row, but... Okay, anything else? Which technique or techniques require that a call setup must be made? Where do we make a call setup? It's more than just one network, one technique, yeah? Next, yeah?
Virtual circuit and circuit switching.
Yeah, both. Virtual circuits and circuit switching. The older one is the circuit switching, the new one. Which technique is flexible? i.e., routing will change as traffic loads in the network change. Like traffic loads sometimes change. One part of the network becomes busy. So routers start directing traffic to the other direction. Which switching technique? Datagram switching technique. Because they're much quicker. While with the virtual circuit, you set up a call, it does not change. Which technique is ideal for short-lived bursts of traffic? That means we get a lot of traffic for a short period of time and then we go a little bit quiet. And less suitable for long-lived or interactive bursts of traffic. Okay? How about you? Sorry. Guys, you can put your hand down. I'll pick the ones who are less enthusiastic. So pretend to be, you want to answer. Put your hands up and say, no, leave them, this guy. Okay, which one was, I forgot the question. Which one is good for long, let's say, always we need lots of traffic all the time for like watching a video, basically. For a long period of time, we have a lot of traffic. This is the second part of the question. Which one is more suited for that? Datagram or virtual circuit? Okay, virtual circuit is more suited for long-lived. Which technique is the fastest to transmit large amounts of data? I have large amount of data, I want to send it. I have a huge amount of data I want to send. Will I use datagram or virtual circuit?
Virtual circuit.
Why?
So first of all, it takes a while to make the connection, but the rest is done very fast.
Yeah, and because we have a huge amount of data, that means we're going to have an hour or two, a long time. So with the datagram, even if it's not busy now, and it could have a good quality of service, but over a long period of time, there's no guarantee it will maintain that. So, which technique is the most inefficient of the three? Inefficient. That means instead of just carrying data, it's carrying a lot of other rubbish as well. So it's not very efficient. Of the three, it's utilizing the link or transmission capacity. Or even utilization. Now this is the question of utilization. Are you using the link to its maximum capacity or not? So which one is less efficient? Or
circuit switching. Circuit switching.
Circuit switching. Why?
Because dedicated.
Because it has a dedicated link, and dedicated links rarely are used 100% to their full capacity. The shared are always more. So, right, okay. In which technique is it likely that packets may arrive out of sequence packets arriving out of sequence. I have somebody volunteering out there. Thank you. You can put your hand down. Thank you. If we get stuck in a question, I'll come back to you. Datagram is more likely to arrive. Yeah, it's possible that it might arrive out of sequence. It may, yeah, that's right. Yeah. Which technique uses? There's only 200 questions here, guys. Let's finish. Which technique uses acknowledgements of packets received as an integral part of its operation? The datagram or virtual second? Which one gives you guaranteed acknowledgements? Tells you if this packet was lost or received. Datagram? Or virtual second? Which one will give you acknowledgement? Well, go for which one does not give you any acknowledgement. Which one does not give acknowledgement? Does not do error detection? Was his answer correct? Okay, neither did I. Say it again. Okay, I'm gonna ask someone else. I'm gonna transfer the question. Okay. Yeah, do you want to answer?
Which one? Use acknowledgement or not?
Yeah, give me either one. Tell me the one that does not provide acknowledgement.
Does not. Datagram.
Datagram.
Okay, I thought it was the acknowledgement.
Yeah. Okay, which one gives you acknowledgement? If you send a message, it comes, I can say your message is delivered. Which one? Yeah. And the one that does not give acknowledgement is the datagram switching technique. Okay? Right, which technique is more suited for broadcasting or advertising? Advertising. Yeah, the back line, yeah? Why? Why the virtual circuit is not suitable? Because there is a broadcast. Because you have to call every individual. Usually if you want to send a message to 10 million people, it will take a long time to call 10 million, to make 10 million calls. It's easier just to broadcast with the datagram. In which service is the quality of service guaranteed? Datagram or virtual circuit? Okay, that's it. Thank you, guys. See you next week.